Today we'll be looking at velocity as a vector. So we can recall here that velocity is speed with a direction. So velocity vectors can be added. So the same rules apply here for all of our different adding, subtracting, our scalars, talking about our different vectors when talking about velocity. So an example here, when you walk forward in the aisles of an aircraft in flight, the 2 kilometers per hour velocity of your walk adds to 500 kilometers per hour velocity of the plane, making the velocity 502 kilometers per hour. However, they are not always in the same direction, so you need to make sure to note that. So in our first example here, if you were walking at a rate of 6 meters per minute on a moving walkway, and the walkway was moving at a rate of 2 meters per minute, how fast were you moving? So you have these two different velocity vectors. So you have one here that is your 6 meters per minute. Then you have your 2 meters per minute. So therefore, a total of 8 meters per minute, because you're able to just go ahead and add them because they are in the same direction here. Now let's look at example 2. So Daniel, the canoeist, can paddle at a speed of 5 kilometers per hour in still water. He wishes to cross a river 400 meters wide that has a current of 2 kilometers per hour downstream. So part A, if he steers the canoe in the direction perpendicular to the current, determine the resultant vector. So let's give ourselves a little visual here. Alright, we're talking about canoeing, alright, across 400 meters. So that's 400 meters there. And we know that there's a current, alright, coming down at 2 kilometers per hour. And we also know that he's going to paddle in a perpendicular from that current. So he's paddling over here at 5 kilometers per hour. So what we have here, so this is just our little visual of our paddling and the canoeist and trying to get across. So when we do this, we have our vector here, which is our 5 kilometers per hour. Okay, so that's the speed that Daniel is paddling at. And then we have our vector that is going to be downstream. So remember, when we're adding, okay, we do it from our tail to tip, and then so on. And this is our 2 kilometers per hour. Now the question's asking, determine the resultant vector. So this here is our resultant vector, so we'll just call that r. And this will be our angle theta. So to find r, we're just going to use our Pythagorean theorem. So r squared is equal to 5 squared plus 2 squared. So r squared is equal to 29, and therefore take the square root of both sides, and we get that our resultant vector is 5.4 kilometers per hour. But we also need to have an angle, because remember, velocity is speed with direction. So we're looking at tan theta, because you're going to use your known, so your 2 and 5 is equal to your 2 over 5. Then you can do the inverse of tan of 2 over 5, so you get that theta is equal to approximately 22 degrees. So therefore, Daniel crosses at 5.4 kilometers per hour at an angle of 22 degrees. So let's move on now. Now in part B, we want to find the point on the opposite bank where the canoe touches and the time it takes to get there. So what we have here, in part A, we were given the distance across, and we were also given the speed that we were traveling at. So using our angle or our triangle that we found 22 degrees, 5, 2, and 5.4. So this was the found triangle from our previous part of this example. And we can look at this triangle here, and we know that he's paddling at 5 kilometers per hour trying to get across 400 meters of water. And we'll call this X and Y. So why do I draw this? Well, I'm going to use my similar triangles. So when we're dealing with similar triangles, you look at the corresponding sides because these are the same shape here and sizes. So what we're going to do, let's find X first. So X over 2 is going to be equal to 400 over 5, and we're going to get that X is equal to 160 meters. We also need to find our Y value, okay? So our Y is going to be equal, Y over 5.4 is going to be equal to 400 over 5, and we're going to get that Y is equal to 432. Now, one other thing that we need to do here, so we know that he's down, okay, 160 meters, all right? And also the distance, the angle distance is 432, and that's the path that he would have traveled. We also want to know the time, okay? So our time is equal to our distance over our velocity. So our distance is 432. And what is our velocity? We know our velocity is 5.4 kilometers per hour, but we need to have it in the same measurements, and since we have our measurements in meters, we need to change that, so it's going to be over 5,400, which is equal to 0.08 hours. So to convert that to minutes, we just take 0.08 and multiply it by 60, and you're going to get that it would have taken 4.8 minutes. So make sure to finish that with a therefore statement. Now in part C, we want to suppose that Daniel had wished to travel straight across the river. We want to determine the direction he must head and the time it will take for him to cross the river. So what we're saying is that he has a force here, all right, so 5 kilometers per hour. But we also know the downstream force, which is 2 kilometers per hour. And then we want to look at what would my velocity here be, and our angle. So our first step is that we're going to find our angle. So we have sine theta is equal to 2 over 5. And the reason that we are going up, okay, so northeast, is because we know with the downstream current it's going to push us, so we know we need to start paddling up that way since it's going to push us down, and so that we can go straight across. So we're going to get that our theta is going to be equal to 23.6 degrees. Now our second step here, we want to find our velocity, so we're just going to use our Pythagorean theorem, so 5 squared minus 2 squared. And when we do our calculations, we're going to get that as 4.6 kilometers per hour. And then our third step, we want to find our time. Our time is equal to our distance over our velocity. Again, you need to change that velocity. So it's going to be 400 over 4,600. So that's from what we found in part 2 of this question. And this will be equal to 0.08696. Now if you multiply that by 60, you're going to get that it was 5.2 minutes. And now in our last example here, an airplane is heading northwest at 500 kilometers per hour, encounters a wind of 120 kilometers per hour from 25 degrees north of east. Determine the resultant ground velocity of the plane. So what we have here, let's draw this out. So if we draw our compass here, we have north, east, south, west. So the first thing it tells me is it's heading northwest at 500 kilometers per hour. So we have this here. It's our plane traveling at 500 kilometers per hour. And since we can look at our plane here, and since it's heading exactly northwest, we know that this would be 45 degrees, and similarly on the other side as well. Now, another thing that it tells me here is that it encounters a wind of 120 kilometers per hour from 25 degrees north of east. So what we have here, we have our wind here, and this here is our 25 degrees. So since we know that is 25 degrees, this therefore would also be equal to 25 degrees. And what we can do here, so this is our wind, we can actually go ahead and draw in our wind vector up here, okay? Because we want it to be from our tail to tip, right? And we want to determine the resultant vector. So my resultant vector is going to be along here. So therefore, I also need to look at my different angles that are given. And actually, I'm just going to draw another picture here, so it's a little bit easier to see. And this here is our 500. This here is our 120. We're going to call this our vector V, and this will be our vector W. So this vector down here, our resultant vector, is W, or V plus W. And what else do we know here? We also know that this angle measurement right here is going to be 110 degrees. And the reason that we know that is because it comes from the fact that we know that this here, this angle measurement is 65 degrees. And since we know that there would be a vector here, this is 45 degrees and this is 45 degrees. So if we were to take this vector here, so I'm going to highlight it for you. So if we were to take that vector, which we did, and we moved it up here, so that's our wind vector, you can notice that this angle measurement, so the 65 plus 45, is the same as this one here, which is our 110 degrees. So that's where I get my 110 degrees from. So what we can use now to solve for our V plus W is our cosine law. So we have V plus W squared is equal to 120 squared plus 500 squared minus 2 times 120 times 500 cos 110. And when I do all my calculations and then take the square root, I'm going to get V plus W is going to be equal to 552.7 kilometers per hour. So the last part of our question here is we need to actually find what the angle measurement here, okay, is. So what we're going to call that is our beta, okay, and beta here is equal to our theta, which this angle measurement is theta. this one here is our theta, plus 25 degrees. So we can go ahead here and solve for that. So we have sine beta over 500, so this is just using our sine law, is equal to sine 110 over 552.7. And therefore we get that beta is equal to 58.2 degrees. So therefore theta is equal to 58.2 minus 25, which is equal to 33.2 degrees north of east.